Welcome back to Electrochemical Engineering. Today I'm going to talk about capacity and cell characteristics of batteries. The plot on the left shows a Ragona plot. The Ragona plot shows the specific energy, that is the energy in watt hours per kilogram, specific means per weight, versus the specific power, that is the power coming out of a battery in watts per kilogram. You can see that any given battery technology has a certain range of powers over which it can operate and deliver close to its full capacity. However, when you drive the reaction fast enough, the capacity of the battery goes down. The energy of the battery goes down. We'll talk about how to think about this in the coming lectures. Here's another curve that actually shows the discharge characteristics of a lithium-ion 18650 battery, a commercial battery that I pulled off the internet. You can see that the voltage decreases as you discharge the battery faster and faster. The capacity also decreases. All these processes depend on the temperature at which you run the battery at. So let's get some definitions. The capacity is a rating of the charge or energy stored in an electrochemical cell. It has units of typically amp hours or watt hours. Amp hours is the capacity in terms of coulombs of charge available. If you remember, an amp equals 1 coulomb per second. So an amp for an hour is a total amount of charge passed. Watt hour is the capacity in terms of energy available. If you remember, a watt equals 1 joule per second. So a watt times time is going to be an energy. These two parameters are related by the average voltage, V average, of the cell by this equation. Capacity in watt hours equals the capacity in amp hours times the average voltage. The capacity is directly related to the amount of active material in the cell. Just to remind you, again, amps equals coulombs per second. Therefore, 1 amp hour is 3,600 coulombs. I'd prefer if we just use coulombs as our unit of charge for battery science, but traditionally it's given in this unit amp hour, which tells you how much current it can deliver and for how long. The theoretical capacity of an electrode can be determined from the electrode reactions and the mass of the electrode. The theoretical capacity is given by the mass of the electrode, Mi, times N, the number of electrons transferred in the balanced chemical equation, times Faraday's constant, divided by the molecular weight of the active material. The theoretical specific capacity is the capacity derived in this way from a chemical reaction for the battery, normalized to the mass of the active material only. So it doesn't include that of binders or other electrode components, the collector and packaging. The theoretical specific capacity can be calculated for the entire cell by setting the charge capacity for the positive and negative electrodes to the same value. That is, the electrons that come from one electrode, the negative electrode, during discharge need to go to the positive electrode, and they must balance. So a balanced battery needs to have equal capacity at both electrodes. Let's do an example. This is illustration 7.1 in your book. The question asks to calculate the theoretical specific capacity of several electrodes. The first electrode is the nickel hydroxide electrode. Here you have nickel oxyhydroxide being reduced by an electron, water, to make nickel hydroxide. This is a 1 electron process. We can calculate how much capacity, how many milliamp hours, are stored in 1 gram of this material. We take 1 gram of the reactant, nickel oxyhydroxide, and we can calculate how many moles that entails by dividing by the molecular weight. There are 1 electron per mole of nickel hydroxide, so N equals 1. And there are Faraday's constants, coulombs per mole of electrons. This gives us the answer in coulombs of charge. Then we have to convert from coulombs to milliamp hours using this unit conversion here. This yields a final answer of 292 milliamp hours per gram for this electrode. We can calculate other electrodes in similar ways. Here, for example, is lithium intercalation into carbon. This electrode has 372 milliamp hours per gram. Notice the zinc electrode. The zinc electrode has particularly high capacity because it's 2 electrons per zinc. The calculations in terms of carbon and zinc are given here. Make sure to go through these and understand how these calculations work. The second part of this example asks you to calculate the capacity of a complete silver zinc cell using the information from the previous problem. You can see from the overall electrochemical reaction for this battery that every mole of zinc must react with 1 mole of silver oxide. We can calculate the moles of zinc based on its molecular weight and calculate how many moles of silver oxide we need for this equation to balance. So the total active mass material is simply the sum of the silver oxide mass plus the zinc mass. Then we can calculate the capacity per gram of total material. We know from our previous problem that we have about 819 milliamp hours per gram zinc, and that we have 1 gram of zinc for every 4.5 grams of active material. This gives us a theoretical specific capacity of 180 milliamp hours per gram of active material that includes both zinc and silver oxide. Now, of course, this is not all the material in the cell. This doesn't account for the electrolyte, the separator, or the current collectors. This is therefore the theoretical capacity. We also want to be able to quantify the available capacity remaining in a cell while in use. And we quantify this in 2 ways. One is called the state of charge. The other is called the state of discharge or depth of discharge. For the silver zinc battery example, at 100% state of charge, i.e. fully charged, pure zinc and pure silver oxide are present. That's on this side, 100% state of charge. As the reaction proceeds, reactants are converted into zinc oxide and silver. You can see this is the reacted volume as the battery discharges. And that is decreasing the state of charge as I move from 100% state of charge to 0% state of charge when the reaction is completely consumed. I talked earlier about whether or not this battery might be made rechargeable. It's challenging because of the low electronic conductivity of zinc oxide. So quantitatively and simply, the state of charge is just the available capacity remaining, for example, in coulombs or milliamp hours, over the total capacity the battery had at the beginning, multiplied by 100% to put it in percentages. It's difficult to measure state of charge once a battery is fully assembled, but it's important for battery management systems like you have on your laptop that tells you the health and remaining energy density in your battery. One exception is the flooded lead acid cell. In this case, the electrolyte is actually involved in a discharge reaction. We'll see that very shortly. And thus, the actual electrolyte changes density with state of charge. So that's an easy way to assess state of charge. Simply, the state of discharge is just 100% minus the state of charge in percent. Now let's look at some cell discharge curves. On the y-axis here is the cell potential, and here's the fraction of capacity discharged. So this is 100% state of discharge, and this is 100% state of charge. What you can see here is at 0 fraction discharged, the voltages are different for all these batteries. Now, why do you think this is? Well, this is related to the thermodynamics of the overall chemical reaction, right? Delta G equals NFE, negative NFE. You'll also notice that the cell potential decreases with decreasing state of charge. So typically the cell potential goes down. You'll notice that some of the curves are fairly flat, like lead acid and lithium iron phosphate, while some of them are sloped. We'll talk about where that comes from. The other thing you'll notice is the big difference in battery voltages between the lithium ion type batteries that work in organic electrolytes that can get to large voltages because the organic electrolytes don't get decomposed easy, compared to the aqueous battery electrolytes, which are limited to about 2 volts. Now, in principle, water is electrolyzed at 1.23 volts, but the kinetic overpotentials are sufficiently slow. The kinetics are sufficiently slow. The overpotentials are sufficiently high, for example, on the lead acid battery, so it doesn't self-discharge and consume electrolyte very fast, even though it's charged at 2 volts. It's worth considering why flat discharge curves are more desirable than sloped discharge curves. Flat curves indicate that there's a steady voltage during discharge, i.e. the voltage doesn't change much. Sloping curves mean the voltage is changing during discharge. So let's use the example from your car battery, your 12-volt car battery. Imagine your car needs 12 volts to run properly, to run the electronics in your car. Once the battery voltage drops below about 1.98 volts per cell, that is, there are 6 cells, wired in series to give you a 12-volt battery, your car won't receive enough voltage to power and the electronics to start. A flat curve will maintain that minimum voltage threshold longer than a sloping curve. Here you can see actually the total voltage at 100% state of charge for a 12-volt battery is actually closer to 13 volts, about 2.12 volts per cell. As the state of charge decreases, you can see by 12 volts, you're at about 50% state of charge. So when you measure your car's battery and you get somewhere close to 12 volts, you're actually only about halfway charged. Let's return and discuss why some curves are highly sloped and some are flat. You can think about the equilibrium voltage of an electrode being governed by the Nernst equation. Remember that the voltage that you measure in a cell is E cathode minus E anode. Both the cathode and anode can be described by their own Nernst equations and have terms in them representing Q. Now, the Nernst equation uses activities and not concentration in Q. So the activity of a solid is 1. So even if the amount of solid changes, the activity is still 1. This is important for so-called two-phase solid systems. In this example, lithium iron phosphate, as you insert and deinsert lithium, the system is always in two phases. In both phases, both the lithiated iron phosphate and the delithiated iron phosphate have activities of 1, and so the potential changes very little with the state of discharge, with the amount of lithium. Remember, this is some amount of lithium which is changing as you discharge the battery. However, the lithium NCA, nickel cobalt aluminum oxide battery, as the lithium content changes, that lithium is inserted as a solid solution where there are not two separate phases. And when there is a solid solution, the activities change as a function of the lithium concentration, and hence the cell potential changes. So let's look at another example. Here's the lithium manganese oxide electrode, which you may have looked at the voltammetry of in the last in-class assignment. The total cell potential is given by this black curve here. That's the total potential E cathode minus E anode. The top curve is the potential of the positive electrode. The bottom curve is the potential of the negative electrode. The difference between the positive and the negative is, of course, the overall cell potential of our battery. For the lithium graphite, its potential is increasing as you pull the lithium out, whereas for the positive electrode, the potential is decreasing as you put the lithium in, as you go from charge to discharge. What's interesting here is the shape of these curves. Notice for this positive lithium manganate electrode, there is a well-defined step in the voltage. So what you can see here is the voltage is flat here, indicating there's a sort of solid solution behavior. Then there's a step as you go down and start charging a different redox couple at a different potential. When you charge this second redox couple, the curve is more sloping, indicating solid solution type behavior. For the lithium and graphite, it intercalates or deintercalates in stages. We talked about staging earlier. That's the idea that certain planes, interstitial spaces, galleries between the graphite layers fill with lithium in a certain order. As you systematically remove lithium, it's harder and harder to remove lithium, and the overall cell potential goes down. Let's take a closer look at phases in solid solutions. Here's an example of a solid solution. In this case, the blue and red atoms are completely soluble with each other. And if we change the concentration of blue and red, they will remain uniformly distributed throughout the solid. This is a solid solution. You can think about it much like a dissolved solution where you have uniform concentration everywhere. The other extreme is when you have an insoluble system, a two-phase system. Here, the blue likes itself much better than it likes the red, and the red likes itself much better than it likes the blue. It's sort of like oil and water, and you have phase separation. Here, because this has activity equals 1, and this has activity equals 1, as I change the proportion of blue to red, I don't change the activity of the species. So this is actually preferred for battery chemistry often because you get a constant voltage output profile. Now, of course, you in reality have some partial solubility of red and blue and red that complicates this picture. Now let's talk about C-rate terminology. This is a normalized rate of charge or discharge. It's a little bit confusing, so let's take it slow. C over infinity is the slowest possible discharge. This gives the total capacity of the battery. 1C is the current that would discharge the battery in 1 hour. C over 20 is the rate of discharge, the current draw from the battery that would discharge the entire battery in 20 hours. C over 5 is the discharge current, the rate of current discharge of the battery that would discharge the entire battery in 5 hours. 10C is the discharge current that would discharge the entire battery in 1/10 of an hour or 6 minutes. So higher C rate is faster discharge. Lower C rate, i.e. C over infinity, is the slowest possible rate. That's taking infinite time to discharge the battery. Here are some discharge curves for a lead acid battery. I'll ask you to explain the trends in the discharge curves using thermodynamics, kinetics, and transport in class. You can see both the initial voltages that you measure depend on the discharge rate, faster discharge, slower discharge, as well as the total capacity, and the voltage at any given point depends on the discharge rate. I want you to think about this in terms of fundamental thermodynamics, fundamental kinetic processes, and transport of species within the cell. Let's define a few more terminology. The equilibrium potential, which Fuller and Harb define as U, is the potential of the cell described by thermodynamics. The potential depends on the material's temperature, pressure, and composition. This is purely a thermodynamic quantity that you can derive from the delta G's of formation of the various species involved in the chemical reaction for the battery. Now, the open circuit voltage is not necessarily equal to the equilibrium potential. Why is that? Well, the open circuit voltage is the potential of the cell when no external current is flowing. It's not necessarily equal to the equilibrium potential because there might be some internal current flowing, i.e. a self-discharge current flowing between the positive and negative electrode that lowers the open circuit voltage from the equilibrium potential. The nominal voltage is the typical potential of the cell during operation at a given rate. This will always be less than the thermodynamic potential when discharging and less than the open circuit potential, which is the voltage of the cell with no external current flowing. The average voltage is the potential generated over either a discharge or charge on average, and the end or cutoff voltage is the potential of the cell when the discharge is terminated. Here's some data from a recent paper by Jeff Dahn, Dalhousie University. He's a major battery researcher, does a lot of work for Tesla. This is a really nice paper showing a wide range of testing results for very high performance lithium ion cells. And this has been used to predict that you could, in principle, run a lithium ion battery for 1,000,000 miles in an electric car before it needs to be replaced. So here they've actually measured over 1,000 cycles, the charge discharge curves as a whole function of a lot of parameters. And what's impressive here for the right battery chemistries and cycling conditions is the capacity decreases fairly small amounts over these 1,000 cycles. The other thing that's useful here is it shows the value of being able to use coding and programming to automatically analyze huge data sets and extract fitting parameters to describe what the various cells are doing and how the parameters are changing over the cycle number. Let's do a little bit deeper dive into the current voltage response of a battery. During discharge, the cell potential is always lower than the equilibrium potential due to overpotentials. This equation relates the equilibrium potential to the actual cell potential. The difference between the two is just the sum of all the overpotentials. The overpotentials generate heat. They're current running through equivalent resistors, dissipating power as heat into the cell. There are ohmic overpotentials. Those are due to the transport of ions and electrons. There are kinetic overpotentials here, kinetics, electron transfer, and ion transfer at each interface in the negative and positive electrode. There's also a concentration overpotential due to polarization and gradients in concentration that develop. We've learned about all these overpotentials in our fundamental advanced electrochemistry course. So what happens if the power is V times I? What happens as you pull more current from this battery? Well, as I pull more current, the power goes up, but the voltage goes down. When the voltage goes down, that means that more of the free energy stored in the battery is getting converted to heat, driving all these kinetic, ohmic, and concentration transport processes, and we have a lower efficiency of our discharge. Let's go through illustration 7.2 in Fuller and Harvey. Here he says, in the absence of concentration gradients, calculate the potential across the separator of a lithium-ion battery. In the absence of concentration gradients. The thickness of the separator is 30 microns with a porosity of 0.38, that's the void fraction, and a tortuosity of 4.1. That means the ions have to move 4.1 times as far as the nominal thickness of the membrane due to the curving paths that the ions have to take. The conductivity of the electrolyte is 9 millisiemens per centimeter, and the current density is 50 amps per meter squared. We can calculate the ohmic overpotential as the current times the length of the separator divided by the effective conductivity. The conductivity, 0.9 millisiemens per centimeter, is converted into an effective conductivity by dividing by 4.1 the tortuosity and multiplying by 0.38, which is the porosity. When we do this, we calculate that the total voltage drop is about 18 millivolts. Now, if we assume for this cell that the area is 0.14 meters squared, a current density of 5 milliamps per centimeter squared would correspond to a 1C rate for a nominal 7 amp hour battery. Okay, so this is just giving an example of the current that would discharge a 7 amp hour battery in 1 hour. The change in voltage, if you discharge the battery in 1 hour versus 1 hour divided by 18, so 18C is 18 times faster than discharging the battery in 1 hour, is 0.31 volts. So that's the additional loss in voltage due to driving the ionic transport simply through the separator. In this case, this energy would all get dumped into the cell, and the cell would get hot. This is important because degradation rates often increase with temperature. The ohmic loss is in fact the largest source of resistance in a well-designed cell. The ohmic loss is, of course, the loss due to moving ions through the electrolyte and separator. We can write Ohm's law assuming no concentration gradient, where the current is just the conductivity of the electrolyte times the change in electric potential with position. This kappa should really be kappa effective, i.e. the conductivity within the given material, or accounting for the tortuosity and the porosity of a separator or electrode material, for example. The internal resistance of a cell can often depend on the state of charge. And this resistance can change during discharge even without a concentration gradient. So consider the lead-acid battery chemistry. In the lead-acid battery chemistry, you have lead metal and lead oxide in the charged battery, in the two different electrodes. Lead metal is the negative electrode, lead oxide is the positive electrode. When the battery discharges, it actually consumes sulfuric acid to make lead sulfate and water. So the concentration of sulfuric acid is higher in the charged state than the discharged state. You see for a lead acid battery that the internal resistance actually goes down as you charge your battery, as you make more sulfuric acid via the charging process. Notice there's also a change in the equilibrium potential based on the Nernst equation for this reaction. The activity of sulfuric acid and the activity of water are changing as the reaction proceeds. In contrast, the nickel-cadmium battery or nickel metal hydride battery used in many of the Prius architectures don't consume hydroxide ions as part of the reaction. Hydroxide might be consumed at one electrode and generated at the other electrode, so there's no concentration gradient and no change in the electrolyte resistance. Now let's talk about kinetics in a battery, electron transfer kinetics. Kinetic polarization of electrodes is typically modeled by a Butler-Volmer expression. What's important to remember here is the voltage loss over potential is not linear with current density. If you remember the Butler-Volmer expression, it has an exponent of the overpotential. So the current increases exponentially with the overpotential loss. That's represented here on this log current density plot versus overpotential, like you've seen in Bard and Faulkner last quarter. The overpotential losses are most significantly seen at low currents. That's because of the exponential nature of this relationship. Once the driving forces increase sufficiently and the reaction exponentially increases in rate, the kinetic overpotential doesn't increase substantially more as you increase the current density linearly. The kinetics are different at both the anode and the cathode, and it's difficult to differentiate from interfacial transport resistances. For example, ion intercalation resistances, ion transfer kinetics, which have their own overpotential terms. For example, often you need to think about how ions solvate or desolvate. Consider lithium plus going into graphite. Lithium plus is solvated by electrolyte in the solution, and when it inserts, it has to lose those solvation sphere. And losing that solvation sphere has an activation energy and kinetics associated with it. Let's think a little bit more about electrolyte transport in a battery. There are concentration gradients due to the passage of current. So imagine a battery, for example, a lithium ion battery. I have a positive electrode, I have a negative electrode, and I have lithium and an anion salt in the electrolyte. When I am discharging this battery, I have lithium coming out to make lithium plus here and getting consumed lithium plus over here. So the net concentration of lithium in the cell is not changing. The average concentration is not changing, and lithium is moving through this cell. Now, what's driving the movement of this lithium? Well, what's driving the movement of this lithium is an electric potential gradient, an electric field. Now, of course, that electric field will also drive the movement of anions. So the anions will be pushed in the opposite direction of the lithium. But the anions are not consumed or generated in the positive or negative electrode reactions. So what happens to these anions? Well, it turns out they generate a concentration gradient within the cell. Let's think about this. So let's consider this battery. At steady state, the flux of anions, for example, a pF6 counterion, it has to go to zero because it's not involved in the reaction. Of course, there's a net flux of lithium coming out of one electrode going into the other, but the anions aren't doing that. So they just polarize and stop moving. Now, due to the requirement of electroneutrality, this leads to an electrolyte concentration gradient. So the anions will pile up on one side and be depleted partially on the other side. The lithiums have to follow along because if they don't, there'd be a large separation of charge and a large energy penalty. We can estimate this concentration gradient from the transport equation for the anions. So we know that the flux of anions is zero. We can write the flux of anions as carrying the current from the total current, the transference number of anions. Remember, the transference number is the fraction of the current carried by the anions relative to the cations. Faraday's constant for units to get to moles, the charge on the anion. This is the current carried by the electric field, driven by the electric field of the anions. But we know the net flux is zero. So if there's a current driven by the electric field, there has to be a counterbalancing current of anions driven by a concentration gradient that develops. So gradient C, this is the concentration gradient of the electrolyte. I can get the concentration gradient of the anions if I know the stoichiometric number for the anions. Here, V minus, it's the number of anions into which one electrolyte formula unit or molecule dissociates into, times the diffusion coefficient for anions. So this is just the diffusion transport term. These two, in a simple way, need to balance so I can calculate the concentration gradient of electrolyte that develops in this cell. And what you see is it increases as you increase the current density. So what's happening is I drive more current through this cell. The anions polarize, they drag across lithiums with them. The lithiums are continually moving through the cell, transporting from negative to positive electron. That concentration gradient in electrolyte leads to substantial effects, important effects in how the cell responds. For example, the conductivity of the electrolyte will be higher on one side than the other. The kinetics of lithium intercalation will change as the numbers of lithium in a local electrolyte region also change. So this is an important concept, and it's related also to concentrated electrolyte theory, which Newman discusses in his classic book in chapter 12, and I encourage you to look more into that. One thing that people are doing is creating electrolytes called single ion conductors. Single ion conductors, instead of having mobile anions, have, for example, a polymer, and the anion is attached to the backbone of the polymer. In this case, the transference number of the anion goes to 0, and you'd have no concentration gradient of anions. This actually improves the performance of a battery, this lack of a generation of a concentration profile under polarization. The total cell voltage is given by the equilibrium potential minus the IR drop, where R is due to all those overpotentials and is lumped into an internal resistance for the cell, and two fitting parameters that have to do with how the cell voltage responds to changes in depth of charge. These fitting parameters, A and B, are purely empirical in this equation. Now let's look at how temperature affects a battery, and in particular, let's look at the lithium ion cell. What you can see here is as you increase the temperature, the voltage of this particular battery increases, as does the capacity. It becomes easier to move ions in and out of the solid, the internal resistance goes down. Those things improve the performance of the cell. However, higher temperatures also increase self-discharge processes. So the capacity decreases at very high temperatures as the self-discharge rate, the internal rate at which electrons can get from the anode to the cathode, from the positive to negative electrode, increases. One thing that's interesting here is you'll notice at 0 degrees Celsius, there's an interesting feature in this cell capacity plot, in this discharge plot. What's happening here is as you start to discharge the cell, it starts generating internal heat. So even though the external temperature might be 0 degrees Celsius, that internal heat is increasing the performance of the battery. Now let's talk about power and energy. Power equals current times the cell potential. P equals I times V. That's one of those things you should have tattooed in your brain. The average power then is just the integral of I times voltage, where voltage is a function of time and I is the constant discharge current, divided by the total time of discharge. Also remember that energy is just charge times voltage. So if I want the total energy of a battery, it's simply this part of the integral. It's the instantaneous power times time integrated over all time. Power and energy are often normalized to mass or volume of the cell. Specific power is kilowatts per kilogram. Specific energy is kilowatt times hour per kilogram. Power density is per liter. Anything that is a density is typically per volume, and energy density is kilowatt hours per liter. You might think about how you expect power and energy to be related to each other in a specific battery chemistry. These are often represented on what's called Ragone plots, like I showed you on the very first slide of this lecture. It shows the trade-off between power and energy. Typically, it's a log-log plot. There's some abbreviations used here: ICE for internal combustion engine, FC for fuel cell, EDLC for electric double layer capacitor, which we'll learn about later in this term. It's a very high power but low energy density electrochemical device that operates as a capacitor. And what you see on this Ragone plot is different regions representing different technologies. Of course, where we want to be is up here. We want very high power. We want to deliver energy as fast as we want, when we want it. But we also want to have really large capacities. Internal combustion engines are particularly good at this. They can burn gasoline very fast, and they can store a lot of energy in chemical gasoline as a fuel. Fuel cells are also quite good. Battery technologies tend to be in this region. You can get fairly high specific energies, though not approaching engines or gasoline, still an order of magnitude less. But you can only get that if you discharge relatively slowly. If you try to discharge too fast, the discharge curves start tending down and you get less voltage out of your battery, and thus you get less energy. Electric double layer capacitors can be charged and discharged very fast. Here on this line is charging and discharging at 3.6 seconds. So if you have a specific energy of 1 watt hour per kilogram and you discharge at 1,000 watts per kilogram, that will last 3.6 seconds. Diagonal lines, as I just pointed out, correspond to a constant ratio of specific energy to specific power. This is called the battery runtime. Battery runtime is just the inverse of C rate. It's how long it takes to fully discharge the battery. You'll want to get comfortable working with these Ragone plots and comparing different technologies and plotting the performance of different batteries in terms of their specific energy and specific power. Another definition that's used in the auto industry is cold cranking amps. Basically, car batteries like lead acid batteries need high currents for short times. You need to optimize that current. Cold cranking amps, or CCA, is the maximum current a battery can sustain for 30 seconds at a specified temperature, negative 18 degrees Celsius. The discharge rate, the C rate, is just the cold cranking amps divided by the capacity. So if the capacity is 35 amp hours and the cold cranking amps you want to deliver is 540 amps, the C rate is just the 540 amps divided by the total capacity, to get, in this case, 15C. So this battery will discharge in 60 minutes divided by 15 will discharge in 4 minutes. So this is the discharge rate during the cold cranking amp test. Finally, let's talk about how heat is generated during charging and discharging of a battery. Q dot, this is the rate of heat generation, which has the units of watts or joules per second. It has two terms. It has one term, which is the current times the equilibrium voltage minus the cell voltage. So where does this term come from? Well, remember, the equilibrium voltage is what thermodynamics says you should get from the cell. It's the free energy available from the chemical reaction. V cell is the voltage you actually get. So any difference from these is due to overpotentials that are used to drive kinetics, mass transport, or ohmic processes within the cell. So this is heat generation due to current flowing through those little equivalent resistors associated with each microscopic process in the cell. The second term has to do with the specific cell chemistry. du, which is the cell potential, U is the cell potential here, remember. dt represents the entropic contribution from the reaction. It can be positive or negative depending on the chemistry. So what this says is when the chemical reaction that forms your battery proceeds, it will intrinsically generate heat or absorb heat from the cell. We can see the du dt represents entropy from this simple thermodynamic expressions. The free energy equals the enthalpy minus T times the entropy of the reaction, for example. G equals negative NF cell potential U. dg dt, therefore, the derivative of G with respect to T equals negative of the entropy. So we can take the derivative of this expression, plug in the term for dg dt as the negative of the entropy, and we can see that du dt is just equal to the entropy over NF, entropy of the reaction. So entropy changes are reflected as heat flows to or from the system or surroundings during the course of the reaction. Now you'll notice that discharge, the current is positive, and V cell is smaller than U, so this term is also positive. You'll also notice that charging current is negative, and the voltage is larger than the equilibrium voltage, so the term is still positive. So no matter what, this term will be positive. It will be generating heat. Here on the left, you can actually see the heat generation rate measured for a lithium-ion battery at different rates of charge or discharge. Higher rates of discharge obviously generate more heat. This is important and plays a significant role in cell performance, system design, particularly pack design, where you have many cells stacked together, battery safety, and usable cell life. One thing to remember is the thermal resistance of cells is actually rather high, so it's difficult to remove heat. So heat management is very, very important. And as we talked about, there's several sources of heat. One is irreversible losses associated with the kinetic and concentration overpotentials, and resistive or Joule heating associated with the flow of current in the solution and electrodes. Joule heating is just another word for resistive heating, like in a light bulb, current flowing through a wire in a light bulb. And there's also reversible heat changes, reversible flows of heat due to differences in the entropy of the reactants and products. So this term here will generate heat, for example, say on discharge, and it will absorb heat on charge. So that's all I have for you today. I'm looking forward to discussing this material with you in class.